In the previous presentations, I've shown how all individual particles were made of photons of the appropriate energy, making 2 revolutions per wavelength. That included the list of properties that all particles would have, such as mass, spin, charge, magnetic moment, chirality, duality, parity, the origins of Einstein's special relativity corrections, as well as the meaning of that world-famous equation, E = mc squared. Next, I showed how that model applied to the only known stable particles of protons, neutrons, electrons, and neutrinos, showing how their structure gives them some of their important properties. But before I start building the universe, it helps to understand the structure and properties of the elementary particles. They are the particles generated when high-energy particles such as cosmic rays and those accelerated in particle accelerators are brought to a sudden stop by colliding with other particles. They are particles like muons, pions, kaons, xi, kappa, sigma, and similar, as they were originally classified as elementary particles when the science was first introduced in the 20th century. They are not the list of elementary particles like quarks, gluons, and bosons forwarded by the current standard model. Understanding their properties and the roles they play in the structure of matter will make it easier to understand the nuclear binding and the structure of nuclei. Knowing that, it becomes much easier to discuss all of these other topics that build the complete picture of the universe, one that I've told you I'll do. To do that, it helps to understand the interchange between neutrons and protons. As was mentioned in my last presentation, they can interchange because a neutron is essentially a neutral proton. This slide shows the decay of an isolated neutron to a proton, electron, and anti-electron neutrino. The residual energy is carried away by the particles as kinetic energy. The neutron, having a higher mass than a proton, can spontaneously decay. Charge, spin, and intrinsic spin are all conserved. Mass and hence energy is balanced by the kinetic energy of the products. The -12 h-bar neutrino means it spins in the opposite direction to the electron. It is an anti-electron neutrino. And that whole process is a normal radioactive decay by beta emission. That is not the only way protons and neutrons can interchange. This illustrates a positron being forced into a neutron to convert it to a proton, while conserving other properties, including spin, intrinsic spin, and charge. The neutrino associated with a positron has +12 h-bar. The electron neutrino is associated with an anti-electron. These following methods that I'm about to show usually occur within unstable nuclei. In this case, there is an excess of protons in a nucleus. That is, they are unstable or radioactive nuclei. Here, when there is an excess of protons, a proton will emit a positron to become a neutron. Spins and intrinsic spins are conserved. The additional energy required comes from the other nucleons in the nucleus. That's an example of radioactive decay by positron emission. This reaction can also occur when there is an excess of protons in a nucleus. A proton captures an electron and is converted to a neutron. Again, conservation of spin requires the emission of a neutrino of the appropriate spin to balance things out. That's a radioactive decay by electron capture. When a neutron decays to a proton and electron, the neutrino is an anti-electron neutrino because it spins in the opposite direction of the electron. When a proton captures an electron to form a neutron, the neutron spin is the same as the electron and is called an electron neutrino. They aren't the only ways for protons and neutrons to interchange. A nucleon, here shown as a neutron, can capture a neutrino and change to a proton by causing it to emit an electron. That requires the neutron to be in a particular energy state that is found in some nuclei. A similar process occurs with protons. They form the basis of some neutrino detectors. The whole point of those illustrations is to show that neutrons don't have protons, electrons, and neutrinos inside them. In the same way, protons don't have neutrons, positrons, and neutrinos inside them. Protons and neutrons are photons of the appropriate energy and polarization state, making 2 revolutions per wavelength. This is a reminder of their close similarity. A neutron changing to a proton, electron, and neutrino is a rearrangement of the rotating photons that produce them. A proton changing to a neutron includes the generation of the 1/27th of a neutron's fundamental frequency. They just happen under the appropriate circumstances. Look, the reaction you won't see is a neutron absorbing an electron or emitting a positron to become an anti-neutron. For a neutron to become an anti-neutron, it requires a neutron's positive core to be negative and its other charged segments to change their polarity. That can't occur without tremendous energy input. There is no need for quarks or gluons of different flavors or colors to explain the transitions between protons, neutrons, electrons, positrons, and neutrinos. They are just part of the rotating photons transiting between various states. It appears that transitioning between those states is not difficult. In all these transitions, energy differences are either obtained from the neighboring nucleons or contained within or given to the particles involved. That is the background needed to understand the origins and purpose of approximately 200 elementary particles that have been discovered from cosmic ray bombardment or generated in particle accelerators. It is that the oscillations in these nucleons easily change to accommodate different situations. Having said that, the topic of elementary particles is too great to discuss in full detail. The best I can do is lay the foundations for others to expand upon, if they should so choose. When particles are accelerated to high speed, their masses are increased and their time slowed down, both by the relativistic corrections. Although their masses are quite large and their time reference is quite slow, they are stable within their own reference frame. A 1 GeV proton has its mass approximately doubled and its time slowed down. A 1 TeV proton will have its mass increased by a factor of 1,000 and its time similarly slowed down. And that applies for all their series of 1/3 frequency harmonic oscillations as well. They are quite stable under their high voltage reference frame. Their internal mechanisms don't notice that anything has changed. Intragalactic cosmic rays from supernova events have traveled for thousands to tens of thousands of years to reach Earth, and they arrive virtually with the energy they started out, and they are to travel that, they are quite stable. When they are stopped by collision with other particles, their masses are no longer in step with the faster time scale at their slower speed. They have to get rid of the excess mass. That can be done by the emission of either linear traveling photons, known as bremsstrahlung, or the emission of rotating photons. They will be known as particles. If a p/9 oscillation were knocked out, it would have the properties of mass, 104.3 MeV per c squared, spin, half h bar, charge, could be either plus or minus e, intrinsic spin of plus or minus half h bar to match their charge. They were the p/9 harmonics illustrated in my previous presentations on protons. But how do they match observation? Muons with a mass of 105.6 MeV per c squared closely match those properties. The only difference is a variation of approximately 1.5% in the mass. That can be attributed to the release of the binding energy of the muon in the proton. Their decay product would be a muon going to an electron plus a muon neutrino and an anti-electron neutrino. These are just rearrangements and emissions of unstable protons rotating photon oscillations. Excess energy in this case is just carried away by the kinetic energy of the particle. Under this model, that would give the muon a rest energy of approximately 0.95 FM. That radius would be reduced to relativistic corrections for an energetic muon. When a muon was jolted out by this mechanism, it would be automatically replaced by another p/9 oscillation as the proton was continually generating them and maintaining conservation principles. Muons are unstable and will decay. The only stable oscillations below low-energy muons are electrons or positrons, depending upon their charge. TeV energy muons would have sufficient energy to decay to a nucleon. I have no idea whether or not that has been observed. The 1/9 harmonic oscillations aren't the only ones that can be knocked out. The presentation on nucleon interchange showed the ease of transitions between protons and neutrons. A proton emitting a muon would find itself temporarily in the same situation as a proton emitting a positron. It would be a neutral particle and would generate a P/27 oscillation. They would have a mass of 34.8 MeV per c squared. Depending upon the circumstances of the collision, that they could have any of positive, negative, or neutral charge. Some of their expected properties are given under the N27 harmonic possibilities. Their mass is 1/27th of the proton's mass. They can have positive, zero, or negative charge as determined by their intrinsic spin, which I have indicated as ISP. They will have their rotational spin of half h-bar. Have they been detected? No, not according to the standard model. Then again, perhaps they haven't searched for it, or by itself it is too small to be detected in the high energies currently being used. However, there is indirect evidence for their existence. Have a look at what would happen if an N/27 harmonic combined with a muon. If the N/27th oscillation increased its mass by 1.5% upon being released from the proton, it and the muon's mass would total about 141 MeV per c squared. Allowing for a bit of binding energy to keep the two together gives the mass a bit under 141 MeV per c squared. As each particle has spin half h-bar, they will either add or subtract. That gives the particle a possibility of being spin 1 or spin 0 particle. Its intrinsic spin, the rotating photon's internal spin, will be 1 h-bar, because there is only one charged particle. The charged muon will keep the neutral N/27 harmonic stable for a while before it decays. When it decays, the spin half h-bar that kept it going in a circle is retained in the photon's rotation, converting it to a muon neutrino. It has a different mass, but otherwise the same properties as an electron neutrino. Now look at the properties of a positive pion. Its rest mass is 139.6 MeV per c squared. The difference is just a tiny bit of binding energy between the neutral N/27 and the charged muon. The two are otherwise indistinguishable from each other. Time now to look at what happens when a charged muon unites with its oppositely charged N/27 oscillation. The two half h-bar spins can unite to form either h-bar or spin 0. Both charged particles will mean an intrinsic spin of 2 h-bar or 0. Oppositely charged particles will be attracted more strongly to each other than will neutral particles to a charged particle. With a stronger binding energy, the neutral particle will have a lower mass. Now look at the properties of the pi-naught neutral pion. At 135 MeV per c squared, its mass is significantly lower than that of the charged pion. This is as expected. All other properties are the same. This time it decays to 2 photons, and this is also expected. The reason why is that the neutral pion decays to 2 gamma rays is because their masses and hence dimensions are quite similar. They are sufficiently close in dimensions and proximity and opposite charge and intrinsic spin that they can unlock each other's spin half h-bar angular momentum. The two travel away from each other in opposite directions, just like a particle-antiparticle annihilation. That does not necessarily mean that the photons have the same 3-to-1 ratio of wavelength. The rotating photons may well have different kinetic energies in motion. I'm hoping that should lead to the inevitable conclusion that pi mesons or pions are a combination of 1/9 and 1/27 of the frequency of the basic proton oscillation. That and the very weak negative charge surrounding a neutron are good evidence of the existence of the 1/27th harmonic oscillation. That gives an insight into what happens to the outer oscillations. Accelerated particles will just generate a shower of pions and muons when they are stopped. The reason for that is that they are particles inside the protons and neutrons that are continually regenerated. But it's now time to have a look at what happens to the energetic nucleons themselves as they are slowed down or stopped. This table shows the protons don't get rid of all of their mass excess associated with their new time zone in one step. It shows protons shedding pions as they adjust to their new rest time zone. They simply cascade from one quasi-stable state to another slightly lower quasi-stable state, emitting pions and muons and the occasional gamma ray until they finally reach a stable state of a proton or neutron. With so many combinations on offer, is it surprising that there are many different pathways for a proton with excessive energy from its relativistic speed to go back to rest when it is stopped? These few selected cascading steps were from a proton that had probably been accelerated to only a few GeV. The symbols under the particle headings are not separate particles. They are protons that have accumulated excessive mass for their at-rest timescale. They keep shedding energy from one quasi-stable state to another until they reach a proton or neutron. And that series started with a proton of mass less than 1.5 times its rest mass and shows how it gets rid of excess mass by shedding harmonics of its structure. Imagine the possibilities as the protons are accelerated to higher and higher energies. They seem quite large. It requires a team of particle physicists equipped with the latest supercomputers to evaluate the results obtained from the latest and largest particle accelerators. That there should be some order in those detected particles should not be surprising. Does that order and those findings mean anything to the overall scheme of the universe? Not really, as far as I can see. They all decay to photons, protons, neutrons, electrons, and neutrinos. They are still the only stable particle states ever detected. I'm not going to take this study any further. There are ample numbers of elementary particle physicists who know the experimental results far better than I do. However, before concluding this presentation, there are some features that need to be explained. A proton is what it is. It's a compilation of series of 1/3 frequency harmonic oscillations of the proton corresponding to the mass of 938.272, etc. MeV per c squared. Accelerating protons to high energies to smash them to pieces and see what they're made of is counterproductive. All that happens is that the original harmonic oscillations are made more massive and their time is slowed down. When they are stopped, the structures that were introduced to them are emitted out of them step by step. Going to higher and higher energies to seek more detail about protons is self-defeating. Finding more and more shorter-lived quasi-stable states isn't proving anything because they were introduced to the proton when they were accelerated. Finding some order in sets of threes is not unexpected because of the series of 1/3 frequency harmonics that exist within those nucleons. Perhaps a better way would be to get high-energy electrons and perhaps positrons, accelerate them to high energies and use them to probe the nucleons. And that is what is already being done and has shown that there are 3 structures close to the center. The proton has 2 positive and 1 negative structure, somewhat as shown in A. Neutrons were seen to have 2 negative structures and 1 positive. They were seen as experimental verification of quarks. Another way of examining the internal structure of nucleons is to get a proton and antiproton at low energies and bring them together. With no possibility of induced structures, the residual will be what the protons are made of. It will be photons. Unlike electron-anti-electron annihilation, in which 2 photons are emitted, it will be a series of photons, perhaps sometimes preceded by muons and pions, and maybe other short-lived structures. The reason for the series is because you have 1/3 and 1/9 harmonics in the proton, and 1/3, 1/9, and 1/27 harmonic in the neutrons. They may not necessarily all combine into the 1 photon at the time of annihilation. That wraps up this presentation on elementary particles. The great achievement of all the accelerators is that nothing but photons and stable particles, electrons, protons, neutrons, and neutrinos have ever been detected and found to last. As for the role of elementary particles in the universe, the 2 longest-lived elementary particles, muons and pions, are structures inside the nucleons. As shall be shown later, they have roles in nuclear binding. As for the rest, which have half-lives between 10 to the minus 10 seconds and 10 to the minus 24 seconds, does it really matter if some order is found in them? In a universe that has survived for over 10 billion years, it is hard to believe that something with a half-life of 10 to the minus 20 seconds is going to have any influence at all on it. Before concluding this session on elementary particles, it is worth a quick look at how this model compares to the standard model. The table and diagram in A represent the latest interpretation of the standard model. Of the required 61 particles, the quarks and gluons, which totaled 44, have never been separately isolated and detected. The W, Z, and Higgs bosons have very short lives and all decay to photons. The figure in A represents the way those various particles are meant to interact. Despite its complexity and claimed successes, it hasn't really helped in the main task of understanding nuclear binding and the structure and properties of nuclei. So limited has been the progress that it has spawned a branch called string theory. It uses 10 spatial dimensions, 7 of which have never been detected, and somehow pretends they're rolled up in tiny little cylinders smaller than Planck's constant. Really, give us a break. It has particles too small to ever be detected and uses mathematics that mere mortals can't understand to make predictions that don't make observations. Compare that to the rotating photon model. There is only one fundamental type of particle, photons. They come in 2 fundamentally different types, those traveling in straight lines at the speed of light, and those traveling in a circle making 2 rotations per wavelength, while also traveling at the speed of light. The former are known as energy, the latter are known as matter particles. There are 2 types of rotating photons. Circularly polarized photons generate charged particles. Plane polarized photons generate neutral particles. There are 3 resonance states in the rotating photons. They correspond to electrons, nucleons, that is protons and neutrons, and neutrinos. Within the nucleons, there are subdivisions of 1/3, 1/9, and 1/27 of the fundamental nucleon photon frequencies. An antiparticle is the particle's photon rotating in the opposite direction with respect to its magnetic field to all of those matter particles. My next presentation will be on the theory of nuclear binding, with the structure of a few low atomic number nuclei being derived. That will be followed by another presentation where the ability to calculate the structure and some properties of any nucleus of any Z and A is presented. Then we can start to build the universe. I'll leave you with some of the topics that will be covered later. If you have any questions on what I've just presented, please send them to Dr. Williamson at jgw@quicycle.com, and I will answer them in a later session. Thank you.